Okay, well, um, let me welcome everyone to the November meeting of the Stockton Astronomical Society, and both in person here in the room in Harmony Grove. Welcome to everyone. I think everyone here is members. I recognize everybody, so there's no guests, but welcome everyone. And then welcome everybody on Zoom. And we'll go ahead and get started with our speaker here and his program. Looking forward to that. Eric will introduce him in just a moment. After the program, we've got time for Q&A to discuss the presentation. Then we've got some announcements, and then we've got one order of business for our elections, and that will kind of wrap up the evening. So let's go ahead and get started then. And Eric, I'll turn it over to you if you want to introduce our guests for the evening.
Thank you, Tim. Our speaker today is Robert Douglas. Since childhood, Robert Douglas has been interested in astronomy and science fiction. He's an active night sky observer using several telescopes he has acquired over the years. He received his PhD in mathematics in 1968 from the University of Washington in Seattle. After spending an international combinatorial year in the Department of Statistics at UNC Chapel Hill, he joined the mathematics faculty at San Francisco State University. Additionally, he has been a member of the computer science faculty since the department's inception in 1983. He remained at SFSU with brief time off for sabbaticals at Harvard and the University of Washington, and to study computer science at MIT on an NSF grant, until his retirement as professor of mathematics and computer science in 2000. He is a member of the San Francisco Amateur Astronomers, the East Bay Astronomical Society, the Tucson Amateur Astronomy Association, the Planetary Society, and the American Mathematical Society. He has traveled to Australia 9 times for its night skies, a journey he hopes all amateur observational astronomers and astrophotographers can make at least once in their lifetime. So please give a round of applause for our speaker, Robert Douglas. Let me hop over to the slides and share them out with Zoom. I'm going to be controlling the slide meeting tonight, and Robert will let me know when to move slides. Let me go ahead and...
I can see the screen.
Okay, let me go ahead and hide my controls here real quick, and I will maximize it a little bit better than that. All right, Robert, it's yours.
Okay, thank you. First, I want to thank Eric and SAS for inviting me to give a talk, because it's always fun to talk to fellow amateur astronomers. And what I'm going to do is talk about, I wrote a book in 2022, the title of which you can see, The Not So Little Book of Astronomical Curiosities and Explanations of Celestial Phenomena. I'm going to give some selections. Basically, there are 59 topics. They're eclectic. So if someone gets the book, hopefully there are a lot of topics that they would find of interest to themselves. And also, there are a lot of facts I give based on calculations. There's an appendix in the back where virtually everything is, all the mathematics is done. That's for those who are so inclined, but for those that are not interested in seeing the mathematical details, since most of them are in the appendix, I think they'll find a lot in the text material of interest. So we can, let me get started here. The next slide, please.
Yeah.
There you go. This is the cover of the book, and the back cover. That's, of course, Eta Carina, which we'll be talking about in one of the topics tonight. So you can get the next slide. Okay, well, part of this was given in the introduction, but there were two main purposes for my writing the book. One was to present, well, in my words, wow topics that amateur astronomers would say, really, I didn't know that. Is that really true? And then I wanted to give explanations for various celestial phenomena. And I list a few of them here, 17 out of 59. There are some topics are longer than others, but here's a sample of some of the topics in the book. The tides, the auroras, the fate of the sun, total solar eclipses, the Saros period, Saros series. Why is the moon tidally locked to and receding from the Earth? What about other moons? Could a moon have a moon? How is the diameter of a star determined? And next slide, just a few more. There's the Yarkovsky effect. There's the illusion of superluminal speed. There's some objects that appear to be traveling celestial faster than the speed of light, but it's an illusion, and there's an explanation for it. And then I'm going to talk about the green flash. That's one of the topics for tonight. There's the Hertzsprung-Russell diagram. Why does one see more meteors after midnight than before? Talk about orbital resonance, and then there's some history. There's one of them that I talk about is about Aristarchus, who lived about 300 before the current era. That's the same as BC. And he estimated the sizes of the sun and the moon and their distances from Earth using geometry and a few measurements. And Steven Weinberg, Nobel laureate in physics, who passed away recently, and who was one of the co-authors of the standard theory in physics, described Aristarchus as perhaps the first modern scientist. He used mathematics and experiment to explain astronomical things rather than appealing to intervention by, for example, the Greek gods. I also talk about exoplanets and then asteroid comet collisions with Earth. Well, those are just some of the topics. And so you can move to the next slide, please, Eric. Oh, a friend of mine who is a very active amateur astronomer and a PhD in physics, Akarsh Simha, he actually created a landing site for my book. And so anyone can go to that website there. I said I wrote 59 topics. There's a 60th one, which is online, free. You don't have to have the book. And it's on exoplanets. There's also a review of the book by Mel Bartels, who's at in Oregon. He's a well-known amateur astronomer. And there's a link to Amazon and then for the book and other information. Okay, so next slide, please. Okay, well, this is the first topic I'm going to mention. It's rather curious. Everyone knows that Pluto's largest moon is about half the diameter of Pluto itself. And there's only 12,000 miles roughly between the centers of the two. So what would happen if you were on Pluto and you looked up in the sky to see Charon, its big moon? Well, a simple calculation that's in the appendix would show that the angular diameter of Charon is about 3.76 degrees. In other words, 7 times the diameter of our moon. So if you look up in the sky and there's our big, beautiful moon, well, 7 times the diameter of that would be Charon if you're looking from Pluto. But it's also interesting. These two objects are sometimes referred to as twin planets. Neither one revolves around the other. The same for the Earth and our moon. There's a center of gravity called a barycenter, and the two planetary objects revolve around that barycenter. Well, for the Earth and our moon, the barycenter is actually inside the Earth. So the moon's revolving around the Earth. But here, the barycenter for these two objects, the center of gravity is actually outside the surface of Pluto. So they're both revolving around that center. So they're sometimes called a twin planet. And they are both tidally locked to each other. Our moon is tidally locked to the Earth, but the Earth certainly is not tidally locked to the moon. And there are no two objects in our solar system where you have the two of them tidally locked to each other than these two. And that presents something rather interesting. If you were on the opposite side of Pluto from Charon, you would never, and you didn't travel, you'd never know there was a moon up there. And if you got in your little Pluto car and drove around the other side, oh my God, look at that thing, seven times the diameter of our moon in the sky. And if you stopped, you would never see Charon rising or setting. It always would remain in roughly the same place, which means, by the way, if you're on our moon looking at the Earth, and you were not moving, you were stationary, you would always see the Earth in roughly the same location in the sky. It's not a circular orbit for the moon, so it moves slightly, but you're not going to see the Earth rising and setting. Of course, if you're in a ship circling the moon, you're going to see it, the Earth rising and setting. But if you're at a fixed location on the moon, facing the Earth would roughly stay in about the same place. And I thought that's sort of an interesting thing for these two very interesting objects. So we can have the next slide, please. Okay, here is one of the weirdest things in the solar system, Miranda. It's the smallest and closest of the 5 major moons of Uranus. If you go out from Uranus, the 5 major moons in order are Miranda, Ariel, Umbriel, Titania, and Oberon. And there's a nice little mnemonic for that, MAUTO. That allows you to remember at least the first letters of those 5 moons. Well, in 1986, Voyager 2 flew by Miranda, took this image. That's the southern hemisphere. It didn't get to see the other side. And the NASA people were shocked because it looks like lots of terrain sewn together, creating a Frankenstein. And there's a famous physicist named Isidore Rabi, who, when the muon, which is a subatomic particle, was discovered and not predicted by anyone, he said famously, "Who ordered that?" Well, the NASA people could say the same thing about this moon. And also, if you're on Miranda, so you're very close to Uranus, well, how big is Uranus going to appear? It's actually about 45 times the diameter of our moon seen from Earth. So there'd be this enormous bluish-green ball, and it's bluish-green because Uranus has methane in its atmosphere that absorbs red light, and so the visible light would be shifted toward the blue end of the spectrum. In this image, I can't point because you can't see me pointing to the screen, so I'll have to talk. There's that chevron, that white V-shaped object right there. That's called the chevron. And if you think of that as an arrow pointing down toward the horizon on Miranda, right in the lower right corner, there appears to be a cliff. Well, that's it right there. That's the highest known cliff in the solar system on any body. We'll be looking at closer images of that in a moment. Some other terrain, there's an oval-shaped terrain on the right-hand side. It looks like the Circus Maximus, the racetrack in Rome. On the extreme right-hand side, it's a very large oval. And it's technically called the corona. Also, on this object, there are some straight lines near the chevron. Straight lines you usually don't see on natural objects, but this is an unusual object. I don't really know why the surface looks like this. There have been some theories, one of which was that at some point, Miranda was in an elliptical orbit, not a circular orbit around Uranus. So there was tidal heating that maybe heated this up, and you wound up having upwelling of soft material that then solidified. But they really don't know. So the next slide, please. Okay, here we have, you can see the chevron again, only it's pointing to the upper part. And if you follow that up to the edge, there's Verona Rupes, the highest cliff in the solar system. And also the Circus Maximus region is prominent in the upper left, that grooved oval-shaped terrain. Really a bizarre object. We wonder what the other side looks like. Next slide, please. Here is my closest shot of Verona Rupes. And so you can get a pretty good idea. It's silhouetted against the black of space right there, and the chevron is just in the upper left. So next slide. Okay, this is there's a fellow named Eric Wernquist who produced a beautiful short film, The Wanderers, written and narrated by Carl Sagan from his book, The Pale Blue Dot, courtesy of Sagan's wife, Anne Druyan. This is an imagined image of the top part of Verona Rupes. And I hope you can see the astronauts standing there on the top, and one of them is actually jumping off, just jumping off. Well, what would happen if someone did that? Let's move to the next slide. Okay, well, just some perspective. On the left is an image of Mount Thor on Baffin Island in Canada, way up there north. It's the highest cliff on Earth. The mountain's about a mile high. The cliff actually drops about 4,100 feet. That's right. And the diagram on the right, that little thing at the bottom is Mount Thor. The cliff actually is 4,100 feet and overhangs at an angle of 105 degrees, which is steeper than vertical. Verona Rupes is 12 miles high, not 1 mile. And to scale, I created this little diagram. And so would you really want to jump off the top of that? Well, and the calculations are in the appendix. If you did jump off, how long would it take you to reach the bottom? Well, remember, this is a small object with a low gravitation, but that's a pretty high cliff. It would actually take 12 minutes before you hit the bottom, and you'd be traveling at 125 miles an hour. Now, maybe if you didn't jump off from the top, but from lower down, but still very high, and you had an airbag, you might survive. But it is a dramatically high cliff compared to what's on the Earth. And so the next slide, please. Okay. Eric told me that the members of your club would be particularly interested in the southern skies. What's in the southern skies? Let me talk about that. So why observe from the southern hemisphere? Well, first of all, just a little background. When I first went to Australia, I didn't know where to go, but I discovered there was the Astronomical Society of New South Wales. They had a dark sky site, and I contacted them, and they had a special person there. His name was Tony Buckley, who was a liaison for foreigners, inviting them to come and look through telescopes there. So I went. And after that, I flew to Sydney, and the dark sky site was northwest of that. And even further northwest is Coonabarabran, which is the real astronomical center of Australia, the Siding Springs Observatory there, the Anglo-Australian telescope. And then there's also a lodge there where amateur astronomers you can rent out the whole complex, set up telescopes in the field, and observe the night sky. And there's an organization called ozsky.org. You might remember that. You could Google it. And they every year have people come to Australia. They meet in Sydney, maybe go out for dinner and see some things in Sydney. And then you go out to Coonabarabran, which is if you were to drive there, I've driven several times. It's a it's a day trip, but they usually take a train to a town called Dublin, or you rent a car and you go. Some people have even flown, but there they have a number of telescopes, and it's a very dark sky sight, and you can get to see the wonders in the southern hemisphere, which are really, truly incredible. And this is pitch black skies. If you look at a map of the Earth and where they show where all the lights are, well, look at Australia, and there are parts of it that are pitch black. I mean, there are only about 25 million people, and 60% of them are in Melbourne and Sydney, Australia. So there are large areas where it's pitch black, which is great for amateur astronomers. At any rate, why am I showing this animal here on this slide? Well, it's the emu. It's endemic to Australia. It's the second tallest living bird after it's the ostrich. And next slide. Okay, well, here's the great emu in the night sky over Tasmania on the left. At the very top is the head. It's basically formed by the dark regions in the Milky Way. The Aboriginal people not only had their constellations, but they actually had figures in the sky based on the dark regions that you could see. And at the very top, that dark region is the coal sack and crux. And then the emu runs all the way down from the top to the lower left. Before the Oz Sky star parties were offered, there was a group consisting of the same Australians, but a group of Texans. And they colorfully called going to Australia and having the star party in Coonabarabran the deepest South Texas star safari. They were humorous. This is a T-shirt, 2007, with this image of the emu in the sky there. So the emu does play a role in this talk. And so next slide, please. Okay, this is a closer image of the coal sack, and you can see the Southern Cross. The Southern Cross, it's the smallest constellation of all 88 constellations you can see from the Earth, but it has two first magnitude stars in it, Alpha Crucis and Beta Crucis. There is no star meeting the cross, forming the cross. Of course, in Cygnus, we have the gigantic Northern Cross, and there is a star that is in the center of the two cross pieces. Here, there isn't. But at the bottom, I can't point to it at the bottom, it's over on the right, just slightly up and to the right of the coal sack. There are it's a diamond-shaped object. Yeah, that one right there, that one right there that you're having, that's Beta Crucis. At the bottom is Alpha Crucis. And there's something interesting if you turn a small telescope on Beta Crucis. If you do that, you will see a very bright carbon star only 2.4 arc minutes west of it. And it's all carbon stars are variables. It's from 8.4 to about 9.9. It's a very bright. Its B minus V value is 5.8, meaning it's about as red as a carbon star can get. And so here in a small telescope, you can see this first magnitude star and very close, this very bright red carbon star. It's quite a contrast between the two. By the way, should I explain B minus V value? It's a color index indicating that's really correlated with the temperature of the star. B stands for the broadband blue, and it excludes blue light, blocks blue light, so it's toward the red end of the spectrum. V is visual, which stands for green and yellow light, which is the center of the visual spectrum for humans. And the B minus V value gives you a rough idea of how red or how white or how blue it is. So this is 5.8, and that's very, very red. I should say one thing about carbon stars. Since they're variable, when they're at the dimmest, they're the darkest red. When they're at the maximum magnitude, there's a little more orange. They're not quite as red. At any rate, this is a particular interesting contrast. So, oh, and the coal sack. Well, you can see now you look at that and it looks like, well, I can see a lot of stars inside it, and you can, but this is a CCD image. But if you're out there even with binoculars or a small scope, that is really pitch black. It's very black, that coal sack. And so let's move on to the next slide, please. This is another sort of interesting oddball object. Just it's called the dark doodad. And by the way, in Australia, they have all these colorful names. Doodad, the dark doodad's vertical streak and musca. And there's a globular cluster at its southern end, that big yellow ball near the bottom. That's NGC 4372 right there. Got it. Okay, next slide, please. Okay, here's another interesting object. You can see this from the Northern Hemisphere, but it's a very nice object. It's much higher in the sky from the Southern Hemisphere. They're a combination of elements. There's the field of nothing. That's a nice colorful name. It's Bernese 157. That's the dark area there, very dark black area. And it's a nice name. And then you have the chandelier globular NGC 6723 up there, pretty big globular, and then various reflection nebulae in blue in between the two. Let me just say one other thing. Everybody knows when you go to the Southern Hemisphere, you're going to get to see all the things you haven't seen before, and you get to learn the Southern constellations. And you expect the Northern constellations to be upside down, and they are. But there's some other sometimes surprising things that might surprise you. I grew up in Seattle where when I got my first little telescope, I had to wait a month before I could see anything because of the clouds. But Scorpius, in the Northern Hemisphere, and certainly in Seattle, I couldn't even see the tail. Scorpius, when it rises, it's head first and then the body and the tail. Same in California. But if you're in the Southern Hemisphere and you're watching Scorpius rise, it rises level. Its body is level, rising above the horizon. It's not head first. So there are these little interesting things that are peculiar to the Southern Hemisphere. Okay, next slide, please. All right, this is my favorite galaxy in the Southern Hemisphere. NGC 1365 in Fornix. It's very, very low here. So it's not really worth looking at, but it is by far the best barred galaxy visible to amateur astronomers anywhere on the planet. It's about 200,000 light years across. Our galaxy is 100,000. It's very bright, and it's also well, I call it the mark of Zorro because it's so in your face. Maybe the two best barred spirals you can see from the Northern Hemisphere is NGC 7479 in Pegasus and NGC 1300 in Eridanus. But you're always, at least I have, even in larger scopes, to see, let's see, where's the bar? I think I can see the bar. Well, this is an in-your-face bar. It is a magnificent galaxy, and there's no question about seeing the bar here. And the actual angular image, visual image is about 50 arc seconds by 40, so it's pretty big. Next slide, please. Okay, my favorite object that you can see from planet Earth. There's nothing like it anywhere, and you have to go to the Southern Hemisphere to see this. It's the star Eta Carina, about 7,600 light years distance in the Eta Carina Nebula, which is an enormous nebula in Carina, well south of here. Surrounding the star is what's called the homunculus. In Latin, that means little man. It's mainly two large bubbles of gas expelled on opposite sides of the star. Now, you would think, well, I'm not going to see that through even a large amateur scope. Wrong. You have an 8-inch telescope, maybe even smaller, you can see those gas bubbles. Because actually the homunculus is about 16 arc seconds by 12 arc seconds. So in high power in an 8-inch telescope, and it appears orange, it's a bright orange bar, and you can see those bubbles very easily. And even I think in an 8-inch, but certainly in a larger scope, you can even see the striations in those two gas bubbles. Those two gas bubbles, they believe, were created in outburst from the star Eta Carina in the 1840s. It's referred to as the Greater Eruption. And then in 1887, there was a lesser eruption where you can see some material coming out sort of perpendicular to that in the upper part there. Yeah, that's it right there. Now, this is a supernova candidate. It's varied in brightness. It's been studied a lot, and but it's been discovered there are actually two stars, not one. One of them is much bigger than the other. And let's move on to the next slide. Here is the two stars. One is referred to as Eta Carina A and the other Eta Carina B, appropriately. And you can see a scale there of about 16 astronomical units. The two stars orbit each other, they think, in about every 5.5 years. And when they get close, that could be sometimes cause the star to become much brighter or maybe even have an ejection. So next slide. Okay, I'm going to show you a little more here. I said that that star with its homunculus is in this gigantic Carina Nebula, which you can see on the left. Now, in the center of that image on the left, there's a wedge-shaped dark region, and above it, there's a bright area. That bright area is where Eta Carina is, the star. And just to the right is a S-shaped, sort of a dark S-shaped object, which is highlighted above the printing on the screen. But you can see, that. And now you can see how Eta Carina is embedded in this enormous nebula. It's called the keyhole. That dark region is called the keyhole. Okay, the next, please. Okay, well, let's talk a little about the Large Magellanic Cloud and the Small Magellanic Cloud. Here we have an image of, and you can see the Milky Way arched across the sky. This is taken from Chile, and you can see the Eta Carina area, that bright area up at the top. That's the heart of it's really the best part of the Milky Way. Whoops, we want to go back. Just right, hold it right there. The Large Magellanic Cloud is down below. It looks like a piece of the Milky Way that's been separated from the rest of it. And then even lower and down to the left is the Small Magellanic Cloud, which is even farther south. The Large Magellanic Cloud is about 160,000 light years from Earth. The smaller one is about 204,000 light years. And the actual distance between the two objects is about 80,000 light years. And so let's move on to the next slide. Okay, this is the Large Magellanic Cloud, what's called the Tarantula Nebula. Okay, what are the greatest objects you can see from Earth? Well, that Tarantula Nebula is one of them. I mean, basically in the south, NGC 1365, you've got Eta Carina, you've got the Large and Small Magellanic Clouds with the Tarantula Nebula, and you got, I'm going to be talking about them, the Omega Centauri and 47 Tucana. Those are objects everybody should see. At any rate, you can see that enormous Tarantula Nebula. I don't have to point out where it is. Can you imagine being, on a planet surrounding a star in a small cloud and looking at that thing? And how big is that? How big really is that? Well, let's move on to the next slide. We'll get a close-up of it, a closer up. Okay, there it is, the heart of the Tarantula Nebula, NGC 2070. The diameter of that is about 1,000 light years. Compare that with the Orion Nebula, 25 light years across. If the Tarantula Nebula were as close as the Orion Nebula, it would cover the entire area of the sky, filling the constellation Orion. Can you imagine looking up at that thing from Earth? And it's about 36 degrees across. And actually, to get some idea, the angular distance between Betelgeuse and Rigel is about 17 degrees. So this would dominate the sky, and every religion and every myth would include this because you couldn't ignore anything like this. So, okay. Let's move on to the next slide. This is in the heart of the Tarantula Nebula. It's called R136. It's a very active star-forming region. This is a Hubble space image. Why don't you go and take a look at that? There's a dark area on the left, and there's that very bright star-forming region on the right, and there's a little red star there, which you can see. Let's just go back to the previous slide and see if you can see that. Now, I wonder if you can look at the heart of the Tarantula Nebula. You can see the dark region. Keep moving on that little, there it is, the dark region right there. Just to the right of it is R136, and the little red star, well, I can see it, I'm close to the screen, but you probably can't see it. That little red star is actually, I can see it. At any rate, this is, of course, the Orion Nebula is 1,500 light years away. This is 160,000. And so the only people that I think would not enjoy looking at this are people with arachnophobia. Let's move on to the next slide, please. And we already saw this, so the next one. Okay, here is a wider field of view, the region around the Tarantula Nebula, which is in the upper center, and the various star clusters, glowing gas clouds, and scattered remains of supernova explosions. So it is really quite an amazing thing to see. So the next slide. Well, we can't ignore the small cloud. There are a lot of interesting things. You can see globular clusters in it and other things inside the small and large clouds. But you can see there are two globulars you can see here. The big bright one is it's 47 Tucana on the upper right. That one, that's 47 Tucana. And then there's another one, that one there, NGC 362. Neither of these globulars is in the small cloud. 47 Tucana is the second brightest globular cluster you can see from Earth. Omega Centauri being the brightest. It's fourth magnitude. You can see with the naked eye. And it is, let's move on to the next slide. Here's a closer image of 47 Tucana. It's really famous for having an incredibly dense core, unlike Omega Centauri, which we're going to look at in a moment. And I might add that 47 Tucana it's about 17 light years, 17,000 light years away. It's in our galaxy, not the small cloud. So let's move on to the next image. Okay, here is a must thing to see. This is Omega Centauri. It's fourth magnitude. It's actually magnitude is 3.65. It's easily seen with the naked eye. Its angular size is about 36 arc minutes, so about the size of the full moon. And it is now known to actually not be a globular. It's considered to be the core of a dwarf galaxy. And there's a lot of evidence supporting that they think that they know there's a black hole in the center, and there are stars of various ages and various ranges in metallicity, and globular clusters, all the stars usually about the same age. So this is a rather amazing object. This is, you know, from Mill Valley in California and from Stockton in May, if you looked at the horizon, you can actually see a little fuzzy spot. You can see this, but of course, it's just a tiny fuzzy spot and you have to know just where to look. But if you're in the Southern Hemisphere, this is an awe-inspiring. It's so big, it's so bright. It contains 10 million stars. This is really big. Next slide. It's about, by the way, it's also about 17,000 light years away. Okay, I say we have 59 different topics in the book, and you can see where, you know, there's a variety here. I'm going to talk about the green flash because there's a surprise here, which even very advanced amateurs, some had never even known is possible. Okay, the green flash, let's talk about it. There's going to be a little geometry. I'm going to try and explain a few things. This is an elusive effect. It sometimes can be seen for a few seconds at sunrise or sunset. Just as the top of the sun reaches the horizon, if it's sunset, then the last rays can glow green. Now, I've many times, you want to look over a body of water, be about sea level maybe. I've looked many times and I've seen it twice, both from a cruise ship and back one day right after the other. So I did get to see it, but lots of times I've looked and I haven't seen it. But a lot of people have seen the green flash. And it usually occurs over when warmer air is close to the ground or water and cooler air is above the warm air. And there's an image of it there, the little green flash. Next slide. I'm going to explain what's going on here, but there's a little geometry. In that upper image, we have the Earth, and then I have the atmosphere in blue, and there's a person on the surface of the Earth right there, that black dot. Now, because light, when the sun is just below the horizon, that lower white globe called, no, not that one, the same upper picture, but to the right, it says sun. When the sun is right there, you can see that that person on the Earth would see just the top, should see just the top of the sun. However, that would be the case if there were no atmosphere. But there is an atmosphere. So a beam of light coming from the sun, that red solid beam would come up, hit the atmosphere and be bent, refracted down toward the observer. And if the observer's there, the observer is going to see the sun by backtracking along the ray that the person's looking at. The dotted arrow is going to show the sun's image above the horizon. Now, this is a freaky, unusual thing. Just when the entire sun is below the horizon, it appears to be just above the horizon. Well, this is because, for one thing, the sun's image is, it appears to be about a half a degree higher than its actual position, but the angular diameter of the sun is a half a degree. So it just works out that when the sun is actually just below the horizon, it appears to be just about to touch the horizon, but still above the horizon. Okay, now I simplified a little bit here. We have that ray from the sun going up, hitting the atmosphere, and then going in a straight line right down to the observer. But that doesn't really happen. In this lower picture, that ray of light comes, it hits the upper atmosphere and curves down to the observer, and then the observer along the dotted line would see that beam of light coming from above. The reason why it's curved is because the atmosphere isn't uniformly dense. It's much less dense in the upper part, so refraction isn't as strong. If the atmosphere were replaced with solid glass, then that beam of light would go in a straight line right down to the observer and not be curved. Okay, let's move on to the next slide. Okay, well, we certainly have to start talking about color here because we're talking about the green flash. And so everybody knows that Isaac Newton used a prism and discovered that white light can be broken into a variety of colors. And when light is refracted, the different wavelengths of light are refracted at slightly different angles. That's going to have an effect here. So here we have a light ray from the sun, that double arrow going up there. It's going to hit the top of the atmosphere. The green light is actually refracted more than the red light. So it's bent more, it's bent down more than the red. Well, an observer on the Earth looking up through the atmosphere, that's going to cause the observer to see the green slightly above the red. Okay, well, by the way, you might wonder, why didn't I talk about blue light? I just talked about green. I'll say something about that in a moment. But of course, I'm only looking at sort of two extremes. Well, blue would be extreme, but red and green. Actually, all of the different wavelengths of light are going to be bent at these different angles. And so you're actually going to, on the Earth, looking up, you're going to have, the result is overlapping red, orange, yellow, green, and blue images of the sun. In fact, all the different colors, all these different images, spheres of the sun are going to overlap. Well, where they all overlap, you get white light. And a sliver of red is at the bottom of the overlap. A sliver of blue is at the top, just above a sliver of the green. I've left the blue ray off because of something called Rayleigh scattering of blue light. We get a blue sky. This weakens the blue sliver produced by refraction. So a blue flash is very rarely seen. I actually was even doubting whether anybody's ever seen a blue flash, but I gave a talk at Golden State Star Party. I had two people come up. They've seen the blue flash more than once, one several times. He was a pilot in Vietnam and he saw it a lot. And the other is a well-known amateur in San Diego. He's seen it a few times. So some people have actually seen a blue flash. But okay, let's move to the next slide. Next slide. Oh, here we are. Okay, I mentioned Rayleigh scattering that causes the sky to be blue. What exactly is that? It's the instantaneous absorption and emission of predominantly blue wavelength photons by atmospheric nitrogen molecules. So here comes a blue ray from the sun. It hits a nitrogen, interacts with a nitrogen molecule, and instead of letting that blue light go right on through to your eyeball, it's going to absorb that and emit blue light in all directions. Well, that's going to dramatically weaken the blue light coming to your eye. So, but the sky is blue because of this. The emissions that occur in all directions. Okay. Here is the image of the sun. I said we have overlapping spheres because of the refraction of the different colors of light. They're different. On the left, we have a big yellow ball, and you get a little green at the top and a little red. And the right-hand image is actually a photograph taken of the Golden Gate Bridge, and there's a little green at the top and red at the bottom. Just one thing. I said that when all the colors overlap, you get white. Well, the sun's yellow. Why is the sun yellow? There's a good reason for that. If you were in the International Space Station or on the moon, the sun would not be yellow. It would be white. The reason is when you're on the Earth, the blue light from the sun is scattered in the sky. So the light that you're getting is sort of missing the blue end. Well, that shifts the light that you're seeing slightly toward the red end of the spectrum, and that means instead of white, it's going to be yellow. So that's why the sun looks yellow. If we didn't have an atmosphere, it would be white. Okay, let's see. I think we're ready for the next slide. Yeah, let's just talk about best opportunity to see the green flash. By the way, how much time do I have? Is that it's 7? I have
It's
I hope I have some more time.
yeah, you probably got like another good 10 to 20 minutes, I would say.
How many minutes?
10 to 20.
10 or 20. Okay, I hope make it 20 if we. I'll try and go a little faster. I better go a little faster. Let's see. Well, I'll just skip over some of this. I will say one thing about photographers. If one is looking at the low orange red sun for a few seconds, it's enough to make most flashes appear green at the stage when they photograph as yellow on color film and I presume CCD images. So most people trip the shutter too soon, wondering why they didn't get a green flash on their image. And one other thing, I thought of this myself. I thought just an intriguing thought. If you were an observer at the North or South Pole when the sun was at either equinox directly over the equator, the sun would circle the sky at the horizon. This could result in intermittent or extended green flashes throughout the day, which would be sort of an interesting thing. But you'd have to be at one of the two poles, preferably the South Pole, because you'd like some maybe variation on the horizon. Anyway, let's move on to the next slide. Okay. All right, here's one of the reasons why I'm talking about the green flash. If you observe the green flash sitting down when near sea level, you can actually prolong the effect by standing up. Would you believe that? That's the shocker. Most people don't know this. Little story. Let me read what's on the screen. In July 2002, a former astronaut, Gariot, was on board the Russian oceanographic vessel and was doing research on hydrothermal vents when a green flash was observed by shipmates on deck 7 and 8. Gariot described, this is in his own words, some observers were on an open portion of deck 7 and others on deck 8, nearby, but 2.85 meters higher. 5 of us on deck 7 saw the usual red disk of the sun change to solid green just before disappearance. We broke into spontaneous applause. The people on deck 8, just above, were still seeing a red disk, and one of them looked down at us, wondering why we were so excited. He missed the green flash, but his 2 partners did see it several seconds after he had. So, now on July 22nd, the observers were stationed on decks 5 to 9, and timings were taken in order to quantify the delays relative to the time of the observation of the green flash from deck 5. The results confirm this delay phenomena. Gariot and his shipmates made a calculation and compared the predicted delays with the observed delays. Let's move on to the next slide. Okay, here's a little geometry. If we look at the geometry here, we've got the Earth and in blue, and there's an observer A, call her Alice, right there. And just above is another observer B, call him Bob. And let's say that the elevation is E meters. B is E meters above A. Now, obviously, this diagram is not the scale because you wouldn't see anything. The distance between A and B is a fraction of the radius of the Earth. R is the radius of the Earth. A would be seeing the green flash along that horizontal red line. B would be seeing, did I say green flash? B would be seeing the green flash on that other line coming right down there. Okay, with a little mathematics, and it's all done in the appendix of the book, we can calculate what the angle of depression of the horizon for Bob is due to his elevation. That's that angle theta up there where B is. Well, there's theta down there. Up there, that's angle theta. That's the angle of depression for Bob due to his elevation above the horizon. Now, geometry tells us that that angle is the same as the theta that we have down there near the center of the Earth. we would like to calculate what theta is in terms of E. If you do the mathematics, it comes out that theta is a constant times the square root of E in radians, which is about 1 radian is about 57 degrees. I'll assume you know what a radian is, but it's not important. So the point is that we know what theta is in terms of the elevation of Bob above Alice. Now, in order to figure out the time difference between the green flashes for Alice and Bob, we have to know the vertical rate at which the sun is descending in radians per second. And then the time is just theta over r. If r is the vertical rate of the sun's descent, then the time it takes between the green flashes is theta over r. So let's move to the next topic. Jariat experimentally determined T by measuring the time between when the sun first touched the horizon to when it disappeared. This was done at his latitude, and it was about 3 minutes. What I have in blue, excuse me, in brown lettering, I'm going to skip. Basically, it's a mathematical formula that can actually give you, even if you're not on a ship at his latitude, you can sit in Stockton, know what his latitude is, know what the declination of the sun was at that time, and you can calculate the angle at which the sun is setting, and from that, you can derive the vertical rate of descent of the sun. But I'm going to skip all that because I'm running out of time. And I didn't want to dwell on the mathematics here. At any rate, the sun's apparent diameter is about 1/2 degree, which is 0.0093 radians. And Gary had timed the vertical rate of descent as 3 minutes. So 3 times 60 is seconds. And we can move to the next slide. So he was able to calculate that the vertical rate of descent was given 5.17 times 10 to the minus 5th radians per second. But the bottom line here is, what's the delay between the flashes? It turns out to be 10.8 times the square root of E in seconds. Now, E is in meters here. That's actually the formula, 10.8 times the square root of E. Now, it's very interesting that the time delay between the flashes is not directly proportional to the elevation between Alice and Bob, but the square root. That's going to have an effect. What I want to do is concentrate on this little table because this is interesting. We're going to compare Bob's green flash time to that of Alice's. We're going to assume Alice is at sea level. The values of E that we consider, I'm going to put them in feet and appropriately change things. I'm going to assume that the value of E, that Bob is 2 feet above Alice or 6 feet above, 100, 104. What's the delay in seconds between the green flashes? Well, it's over there on the right. Okay, 8.4, 14.6, and so on. Well, here's what's really interesting about this. Suppose that Alice is at sea level and, let's see, suppose she's sitting in a chair 2 feet above sea level. She sees the green flash. She immediately stands up, and let's say she's now 6 feet above sea level. The delay in seconds was 8.4 and 14.6. If you subtract 8.4 from 14.6, there's a time difference of 6.2 seconds. Alice is sitting in a chair at 2 feet. She sees the green flash. She has 6.2 seconds to stand up, be 4 feet higher, and see the green flash again. Well, she could stand up in a fraction of a second and just wait 4 seconds or 5 and see the green flash again. Now, just to point out, suppose Alice was sitting in a chair at 100 feet, not 2 feet above sea level, but 100. And then she stands up. Now she's 104 feet above sea level. What's the difference in the delay in seconds? It's 60.8 minus 59.6, 1.2 seconds. She'd have to stand up really fast. So if you want this to see the green flash twice, you want to be close to sea level. So that is sort of an interesting interesting fact. Next slide. Okay. I went through that a little quick because of the timing here, but I want to mention I had two other topics I thought I'd have plenty of time for. Probably there might be only this one. I'll just say a few words about the next one. There are two moons of Saturn that are in virtually identical orbits, and you might think that they would collide, but they actually don't. So it's rather interesting. One of them is Epimetheus, which is the lower left in that image on the left, and Janus in the upper right, as seen by the Cassini spacecraft in 2006, 2 months before swapping orbits. Janus is actually farther away. They're actually much farther away from each other. This because there's foreshortening due to the angle at which this photograph was taken. At any rate, here's the interesting thing. So they are in virtually identical orbits around Saturn. Epimetheus is about 75 miles in diameter. Janus about 112. They're orbiting Saturn in the same direction. Their orbits differ by only 31 miles in distance from Saturn. That's less than the radius of either body. So you would think that since the moon that's slightly closer to Saturn travels at a slightly faster speed than the outer moon, you would think that it would catch up and it would collide because of this, the only difference is 31 miles between the two, and so clearly they would collide given their diameters. Let's move to the next slide. It actually doesn't happen. So what's going on? We'll call it a little dance. Epimetheus, actually, we're going to look at this top to bottom. It orbits closer to Saturn, so it has a shorter orbital period and eventually approaches Janus from behind. If you're closer, you're moving faster. It's going to start approaching Janus. And so we have. Now, what happens when they get closer? Well, they get closer and they're going to start gravitationally tugging on each other. What's that going to do? The tugging is going to slow Janus down and speed Epimetheus up. Well, if Epimetheus speeds up, then it's going to have to move farther. By the way, Saturn would be at the bottom of this screen. Epimetheus, if it's speeding up, it's going to have to move a little farther away from Saturn. If Janus slows down, it's going to have to move a little closer to Saturn. So what happens is, closer to Saturn, Janus speeds up in its orbit, farther from Saturn, Epimetheus slows down. Janus will slowly creep. Janus is now closer to Saturn, so it's going to speed up and pull away from Epimetheus. So you actually never have one of them passing the other. They switch orbits. Let's move to the next slide. Since the total angular momentum of the two moons is a constant, the velocity changes cause the inner moon to moon a little further away from Saturn, the outer moon to moon a little closer. In effect, the two moons switch orbital places due to an exchange of angular momentum. Neither moon actually orbits past the other. The dance takes about 100 Earth days. The two moons actually keep a healthy minimum distance of about 9,000 miles between them. And after about 4 years, they repeat this performance in reverse. And the twins' co-orbital situation is the only one known in the solar system. And you can just imagine if an astronaut were on one of these moons watching the show, it'd be really quite something. Let's flip to the next screen. Okay, this was the last topic I thought I could get to. It's very interesting. How much time do I have? 5 minutes or?
I would say you have probably another good 10 to 15 minutes.
Okay, then we can cover that. Hey, this is really interesting. Well, I think all the topics are interesting myself, but so no surprise. Well, yeah, this is very interesting. We all know what Cepheid variables are, and we know that they're really special because it's been shown that they pulsate. And it's amazing. The pulsation period is related to the average absolute magnitude of the star. Well, we all know what that means. If you see a Cepheid way out there, and you know its apparent magnitude, you measure its pulsation period, you know its absolute magnitude. If you know the apparent and absolute magnitudes, you know how far away it is. Ooh, that's very nice. Prior to the discovery of Cepheid variables, parallax was the main way of detecting the distance between an object and Earth, but it only works out so far. Objects that are very far away, it doesn't work. But here is, if you can detect the Cepheid variable in another galaxy and measure its pulsation rate, you know how far away it is. Let me just say a few words. There actually are three different things here. Two Cepheids plus another type of star that's very similar. They all have this property that the pulsation period is related to their absolute magnitude. There's a type 1 Cepheid called the delta. The classic example is delta Cepheid. And there's a type 2 Cepheid. The classic example is W Virginis. And then there's also another class of stars, RR Lyra. You know why? That's the canonical example. They just called RR Lyra stars. And if you look at the graph relating the pulsation period to the magnitude, the graphs are different for these three types of objects. Say a little bit about the different types of objects. The type 1 Cepheids, they consist of population 1 stars where the pulsation period is between 5 and 10 days. Now, what's a population 1 star? They're younger stars, they're brighter stars, they have a higher metallicity rate than others, and they're found in the disk of the galaxy. The type 2 Cepheids, they're population 2 stars. Population 2 stars are older, fainter, they have less metallicity. By the way, metallicity just means elements other than hydrogen and helium. Then, those elements are not all metals, but they're called metals in this context. And the period here is at least 10 days. And then finally, the RR Lyra stars. They're very lower luminosity stars with a pulsating period that's 1.5 hours to 1 day. Now, let me, a little history here. Henrietta Leavitt in 1908 and 1912 was studying Cepheid variables in the Large and Small Magellanic Clouds. She was working under a person at Harvard, and Pickering, and she discovered this relationship between the pulsation rate of Cepheid variables and their absolute magnitude. Now, how could she tell what the absolute magnitude was? Well, she was studying stars in the large and small clouds. You can get the distance to those stars using parallax. So they knew the distance. They knew the distance, and though they could then get the chart showing the pulsation rate versus the absolute magnitude of the star. And now the whole idea is if you see a Cepheid variable so far away that parallax isn't going to tell you how far away it is, but just look at the pulsation rate and you know what the absolute magnitude is, and that gives you the distance. And indeed, Hubble in 1923 and 24 observed Cepheid variables in M31. And he then could tell how far away M31 was. Well, there was this raging controversy in astronomy. Was M31 this fuzzy spot in Andromeda? Was that actually some gas cloud, nebula, or was it out of this world? Now, what does that mean? It means you look at everything you can see in the sky and you say all of these things are certainly going to be within 60,000 light years of Earth because we know that now. Well, Hubble discovered M31 was 1 million light years away. That settled the controversy. This was not some gaseous nebula at a distance roughly comparable to the other things you can see in the sky. This was a long way away. And in fact, because of this, they didn't realize there were different types of Cepheids and there were some other issues. Actually, it turns out that M31 is 2.5 million light years away. even further. But at any rate, Hubble showed that this was an island universe, probably similar to ours being defined by everything else you can see in the sky. So what Henrietta Leavitt discovered here was absolutely first-rate importance. And she was going to be nominated for the 1926 Nobel Prize by Mitthak Leffler, a Swedish mathematician. But then they discovered she had unfortunately passed away, and Nobel Prizes are not given out to posthumously. So, but she certainly did something that fully deserved a Nobel Prize. Okay, so next slide, please. What I want to do is, and it's an easy thing to do, and this will wrap up my talk. Hey, what's causing this pulsation in Cepheid variables and our Lyra stars? What the heck is going on? Well, there's an easy explanation. Okay, here's an image of the star. There's the core, which is in red. There's the blue is a low density envelope, but in between the two is what's called a pulsation layer, and that is what expands and contracts. Interestingly, the core stays the same size and produces energy at a constant rate. So the core isn't changing. The pulsations arise from variations in the rate at which radiation can escape from the star. And the control mechanism is the pulsation layer, and we'll see the details. Next slide. Okay, there's a little preliminary information you have to know about stars in general, and then we'll immediately apply this to Cepheid variables. Deep inside a star, radiation, starting off as gamma photons, very high energy, from fusion, it actually takes millions of years for those photons to reach the surface, the photosphere of the star. And when it does reach the photosphere, it's ultraviolet light or visible light. It's no longer high energy gamma rays. Once photons reach the photosphere, they stream away at the speed of light. And after spending millions of years to reach the surface, the light takes only about 8 minutes to reach Earth. So why does light spend millions of years navigating the sun's interior? The reason is that photons can stream unimpeded through a gas of neutral atoms, but are scattered by free electrons. Well, in the heart of the star, you're not going to have any neutral atoms. Those atoms are going to have their electrons stripped off them. The hydrogen and some helium in the star is ionized, meaning the hydrogen's lost its only electron, and the helium, it has 2 electrons. It could lose 1 or it could lose both. And so the actual photons are being scattered by all these electrons and ions. And it's a very, very dense, these free electrons and ions are very dense. It's sort of, you could compare the photon trying to escape the star by, let's talk a drunk. But a drunk, he's hanging onto a light post and he wants to go home, and he starts staggering to get away, and he's wandering in all kinds of different directions. He's the photon, and he's wandering in different directions because he's interacting with electrons around. It's going to take him a hell of a long time to walk 2 miles home. Well, it's going to take a long time for the photon to reach the surface of the sun. Okay. Okay, let's move on to the next slide. I wanted you had to know that information, because now we're going to talk about the Cepheid variables. Okay, at the beginning of the pulsation cycle, the PL is pulsation layer. The pulsation layer contains singularly ionized helium. It's helium, it's got 2 protons, 2 neutrons in the nucleus. And if it's neutral, it has 2 electrons, but one of them is missing in singularly ionized helium. The pulsation layer is not hot enough to strip both electrons off of a helium atom. Well, if it's just singularly ionized helium, then there aren't that many electrons in the pulsation layer, but there's still a few, a fair number. And so it allows radiation to pass through the pulsation layer. It's not going to take millions of years. It goes through fairly quickly. But now, some of the radiation passing through the pulsation layer heats up the pulsation layer. That increased temperature is going to cause some singularly ionized helium atoms become doubly ionized, more electrons in the pulsation layer. That's going to block radiation passing through the pulsation layer. And so as this block radiation causes the pulsation layer to expand outwards, and the envelope of the star is pushed out. But as the expansion occurs, the density and temperature in the pulsation layer start to drop. And so the doubly ionized helium atoms recapture an electron, become singly ionized, and gravity and the reduced outward pressure causes the pulsation layer to contract to its former state, causing the star to contract, and then the process begins all over again. And this mechanism was discovered by famous astronomer Arthur Eddington, and he characterized that in his book, the 1926 book, The Internal Constitution of the Stars. And so I made it through this topic. I wanted to get through there. There's some others on the slide, but I knew I wouldn't have time for them, but who knows? If I did, I was ready. Let me just have you, Eric, just go to the very last slide of them all. I just thought I'd throw, yeah, right there. Again, here's this website where you can see topic 60. I'll tell you what it is. It answers the question, if you have a star circling, a planet, an exoplanet, traveling around its star in a circular orbit, and you're on the Earth, what's the probability that you'll see that star, that planet, traverse its star? Well, there's a simple formula for it, and actually there's a very slick way to see why that's true. It's a simple argument as long as you assume that the orbit is circular, and then you can calculate the probability, if it's a circular orbit, that it'll transit its star as seen from Earth. At any rate, I thought I'd just leave this website there, and there are a lot of other topics to look at, and so I picked these out as I thought might be representative and I think of particular interest to the SAS. And I thank you for inviting me for the talk. If there are any questions or...
Thank you, Robert. Does anybody have any questions for Robert?
Is the book still in print and available? Is your book still available?
Oh, absolutely. It's you can just Google the book on Amazon and it'll come up, and this is also, there's a link to it at this website. But if you just Googled the book in Amazon and my name, you'll get it.
Great, thank you.
Sure.
I have a quick question. That last topic you're talking about with the Cepheid variables and the pulsation layer, what is the reason why not all? So it seems like the key is the pulsation layer. Why do not all stars have a pulsation layer?
Yeah. I'm actually, that's a good question. I'm not sure why other stars don't, but it just certainly has to do with that. And I don't know why that's the case. Why does a star develop a pulsation layer? It must have to do with certain physical conditions that I'm not really sure why.
Okay, thank you.
Eric, you've got to read Arthur Eddington's book.
Okay.
Okay.
I'm thinking.
Right.
Yeah. So, Robert, excellent presentation. I so appreciate you not only giving us the phenomena, but then also the mathematical derivation. I mean, it just adds so much credibility to the item you're talking about. So, thank you for that.
Sure. Mel Bartels, by the way, in his review of the book, and he's used the book giving lectures, he said, to various clubs and other presentations. He particularly commented on all of the mathematics in the appendix for those who want to see the details. You know, if people can just throw a formula there, and it's like pulling a rabbit out of a hat. It's magic. How the hell would you ever get that? Well,
Exactly.
I just thought people would maybe like to at least, if they're interested, they can go ahead and look at the details and see how it's done.
So Robert, my question is, I believe it was your first or second slide talking about the relationship of Pluto and its moon Charon,
Yeah.
them being tidally locked. Do you happen to know or can say if they're on the same plane, such that if you're on Pluto, would you have a daily solar eclipse?
A solar eclipse.
Such that the moon eclipses between the sun and Pluto?
Well, let me think here. Well, I mean,
The relationship.
it does, would the relationship cause Charon, if you're on Pluto, to see Charon cross the face of the sun? Is that orbital plane? I don't know if the orbital plane is in the same orbital plane as Pluto. Probably, it may very well be. Of course, the sun is going to be very small from Pluto, so Charon would just completely block it off. It wouldn't be transiting the face of the sun. I suspect it would just completely block the sun off because Charon would be so big. It's 7 times the diameter of our moon as seen from Earth, and so it wouldn't cross the face of the sun. It would cult the sun. But it may very well be that, and I suspect it could very well be that the orbital plane of Charon is also the orbital plane for Pluto, in which case Charon would obliterate the sun.
That one spot on, or Charon, because they're tightly locked to each other.
Pluto and Charon have.
I can't hear.
125 years. Because the plane of the orbit is like this.
Oh,
The
sorry.
orbit of Pluto, Charon, so every 125 years, they'll line up.
There we go. Okay. Well, thank you, Robert. Any other questions for our speaker tonight? Okay. Well, then again, Robert, we thank you very much, and
My pleasure.
appreciate your presentation. Let's give him a round of applause again.
I thank you all very much.
Thank you, Robert. We're gonna conduct some club business. You're welcome to stay if you want, but you can sign off anytime.
I think I'll go have a
Okay.
dinner.
Okay, very good. Thank you, Robert.
Thank you. Bye-bye.
Bye.
You have questions, or you don't ask?
Great presentation. Okay, Eric, if you'll put up the announcement slide, and we'll press on through our business section of the meeting here. And so let me go through these announcements. I think you all know where to find all the dates on the SAS website for upcoming star parties and public outreach. So the rest of November, this one on the 18th, Doug's got a star party at the Tracy Public Library on Monday. True.
Those is Doug.
So Doug, you got some volunteers lined up?
Casey rescued me. Casey and Richard rescued me.
Okay. Is this a school group at the library? The city of Tracy.
City library in Walnut Grove every year.
Is that right?
And the librarian there moved on and we didn't work, all that.
Yeah. Okay, then November 23rd and the 30th are star parties. Look at the Google Groups email thread if you're interested in coming and see if who's going out and where we're going. Coming up in December, the 6th, we're back at Delta College. That's on a Friday night. The 7th is Astronomy in the Park out at Oak Grove. The 12th is our general meeting here. This is our show and tell, so be thinking about whatever topic or subject you'd like to share with the group. It can be anything from maybe a movie you saw, an article you read, an experience you had. I know a bunch of you went to travel for the solar eclipse this year, so maybe we want to hear more about those trips. Anyway, think about that, whatever you can share for show and tell. The 21st and 28th are our star parties again. January 4th, we're at Oak Grove. We're not doing Delta College in January. And then the 9th is our meeting here. It's going to be our potluck and installation dinner. So more information on that will come out. We'll have a little bit better organization of what dishes everybody will bring. And so look in your email for some upcoming information on the January 9th meeting. And then the February 8th STEAM event, the STEAM Expo is here at San Joaquin County Office of Ed. We always have a good time with a big turnout. There's like over 500 people. This is where the schools throughout the county are submitting their science projects and being judged, and then having their expo that day. So put February 8th on your calendar. And I believe we also have a date where we're going to go to Lodi High School for a STEM event. Do you remember the date of that, Doug? It's later in the month.
Later in the year, and I thought it conflicted with our schedule, to tell you the truth.
Okay. But anyway, those are still a few months away, and we'll
I think
make
it was
those
also-
announcements.
I think it was also in February, but after.
Yeah. So, okay. Hey, did you guys see our Facebook page and Eric's photo of the Pleiades? Absolutely phenomenal detail in the Pleiades. Eric, you took this up at Campo?
No, I took this in Lodi, at my house.
Is that right? Including all the light pollution,
Yeah.
everything right in there, huh?
That was taken with the new Dwarf 3 smart scope. So if you recall back in May, I talked about the Dwarf 2, and this is the Dwarf 3. They're very similar, but I had gotten one. It has some optic issues. It has some diffraction spikes that shouldn't be there. So I had them send me another one, and it seems like it's good. So
Did you post it on Instagram?
it's on Instagram and Facebook. Yeah,
I guess
I posted it last night, like around 11 o'clock at night.
okay.
Because I don't know, visually, can you see any of that nebulosity?
Yes, you can see the line and the little nebula if you have a good scope in the dark side.
Mm-hmm.
The nebulosity is actually in front of those stars. They're not with the stars.
I just haven't.
That
Oh, is that right?
they're just
Nice.
passing through an area with some nebulosity, with some gas and lighting it up.
Accidental collision.
Mm-hmm. Okay, very good.
I have another image if you want to see it.
Sure.
Yes. Just show them all.
Let's see here. So the other night I was out with Casey and Rich. This is the Triangulum Galaxy.
You can see 604 there.
Nice little cool little red nebula right there. Nebulosity. That was taken back on the 2nd. The Pleiades one was taken on this past Sunday.
Mhm.
But both images were imaged for about 100 minutes. This one though was imaged with my new ASCAR 71F. The other one was with the Dwarf 3. So
Yeah. Oh, your tracking's right on because those stars are a real good pinpoint. So
yeah, nice good color in this one.
thanks for sharing that.
Sure.
Okay, if you go to the next slide, then I just have a few more announcements. A reminder to everybody that your SAS dues are now due for next year. The T-shirts are on order and being delivered. We're wondering where the T-shirts are. Okay, great.
Bring your checkbooks, so you can pay Jerry.
I mentioned the show and tell coming up in December. I mentioned the January 9th potluck here. April 5th, we're on the calendar for our Striking Sparks potluck out at Oak Grove. And then we do have our calendar of star parties completed for next year. Eric's going to be putting that on the SAS website very soon. We have one item to talk about. I want to get your input. November 29th is the Saturday right after Thanksgiving. It's our, 2025, November 29th. It's 2 days after Thanksgiving. We're wondering whether we should go to Oak Grove or not that night. So any input? We kind of thought that everybody's traveling out of town, that maybe we would just cancel that. Or does anybody think strongly that we should go ahead and go? Just November 29th.
2 days after Thanksgiving.
Yeah, Thanksgiving's the 27th.
Saturday.
If 5 people go out to the park, we might get some people to come out of the public. But if everybody's gonna be busy, then, or think they might be busy, then I think we should just say we'll not do it 2 days after Thanksgiving. We also have that same problem in December, 2 days after Christmas,
I think that's a bigger deal.
which would, I think it's just not workable.
Why are we going on a new moon?
What's that?
Why are we going to go on a new moon?
It's not a new moon.
The 30th is new moon.
2025.
2025.
25.
Sorry? I'll just stop talking.
No, never stop talking.
That's okay. Well, thank you, everybody, for that lousy input and comment. Jerry?
Most of us were thinking that, it also happens in July, like July 5th is Saturday, first quarter moon, and it's just, yeah, I don't think that's a good idea, so we're not gonna do it in July. Personally, I don't think we should do it 2 days after Thanksgiving, because I don't think we can have enough volunteers and get enough interest from the public. And I think Christmas is also a no-brainer that we don't do it. There are 2 dates in, I forget which month, we'll be doubling up in the month, because we do it on the 2nd, we do it on the 30th or something like that. So, I mean, you know, but there's no, we have to be there once a month.
It's probably gonna be rainy and cloudy anyway.
Okay.
Stay over there, yeah, it's over there.
Yes.
But
Monday after, we're already here, we're June 28th already. And then-
But we're going to take that off the schedule. We're going to take, the only one we're talking about is the November 29th right now. So thank you all for that. Okay, I should have passed this out earlier. It's the refreshment sign up for next year. So I think we still got a few minutes. We'll pass it around. Please sign up. And I didn't invite everybody to help yourself to the refreshments and coffee over there tonight. Okay, then what you all have been waiting for, the elections for tonight. So you all know how this works. These are the nominees. Well, let me start it off and do this properly. The nominating committee was Bill Lytle. Bill developed a list of the nominees and he passed it on to our secretary, Eric. Eric, will you tell us who the list of nominees are?
Okay, so our list for nominees for 2025 for president is Tim Clark. Vice president is Doug Christensen. Secretary is myself. Treasurer is Gerald Hyatt. Newsletter editor, who is down in LA area, is Rebecca Lewis Merrill. And we have two new members of large this year, Patrick Lehman and Omar Anzaldua. And so I would like to ask, so since Bill's not here, I'm gonna kind of take over and say, are there any nominations from the floor for 2025 to replace any of these, to run for any of these positions? Going once, okay. Second time, are there any nominations from the floor?
Dennis,
How about in Zoom?
Dennis raised his hand.
Dennis raised his hand.
Not a nomination, but I move that the board be elected by unanimous consent as presented.
Okay, so one
Thank you.
second on that. I'm just gonna
He's
ask,
getting there.
ask for a third time. Are there any nominations?
He's
from the
getting there.
floor? No nominations. I see no hands, nobody in Zoom. So do I hear a second to Dennis's motion to accept the officers as listed?
I second that.
Okay, Casey seconds it. Any objections from Zoom? No, that's just you, Omar. Okay,
Raised there.
then we're not gonna bother passing around any ballots because we have no other nominations. So we'll accept it as is. Thank you very much.
That was easy. On a sad note, we just got news that longtime member of the club, Neil Lark, just passed away. Yeah, great guy, great guy. Jerry, you probably knew him best. Would you like to tell the club a little bit about Neil Lark and what he did? And
Well, Neil was working on a postgraduate project in Amsterdam when he heard about a new experimental education going on at University of the Pacific. And he wrote that he was interested, and they asked him what the curriculum should look like for this new program. And he wrote extensively on it, and they hired him on this, just through the mail. This has come on out, you're hired. And that was in 1962. He was at University of the Pacific through 1999. He was a professor of physics, where he taught astronomy, physics, of course. He taught physics of music, which was an awesome class in how all types of sounds is made and how instruments are designed and whatnot. And yeah, he was quite expert at all of these things. He was a past president of the Stockton Astronomical Society. He also was one of the key players in getting the SAS involved in what's called a TOPS program with the county office. That's teaching opportunities for partners in science, which was intended to be for retired scientists to go into elementary classrooms. And not only did he help organize that, but he went into many, many classrooms, took time from his schedule to go out to the elementary schools and do that. So, yeah. Yes. Oh, there was a long time ago, the United States was talking about building a superconducting super collider. It would have squashed the Large Hadron Collider that's at CERN over in Europe. It would have been, many times the size and 20 times the energy capacity. And one of the proposed sites was in Escalon. And Neil was, I think he was the chairman of the committee that was pushing to get it here in Escalon. I saw some of the plans for it one time that he shared with me. It was pretty awesome. The super collider lost funding. Congress decided not to build it, so it never came about. But he was dearly loved. He was noted for his attention to detail. Many of you have seen Jim Hetrick from UOP give some presentations here. Well, Neil was the chairman of the department, and the chair of the hiring committee that brought Jim Hetrick to UOP. And so he had kind of taken Jim under his wings to train him to be the new chairman when he came in. And Jim said he got to look at some of Neil's notes for when he prepared a lecture. And he said the top of his notes were, "Hi, my name is Neil Lark." He didn't want to forget any details at all. So he was very meticulous in everything he did. And yeah, he's also how I came to UOP as a student. So he was the first faculty member I met, and I was very, very impressed with his presentation in the program there. So he will be missed. Liz has mentioned that a service will be planned, possibly the first weekend in December 7th and 8th. She would like to have it at Morris Chapel. That was one of his favorite buildings on campus, but no plans have been made at this point. Anyone else?
So yeah, kind of a sad note, but on a little bit better news is the next slide. I do have some good news for you. Okay. Somebody tell me why 8 minutes is the time when. Right. So I think that concludes our meeting for tonight. Is there any other comments or input from anybody that you'd like to share? So, okay. Mike and Doug, thank you for the coffee tonight. Eric, thanks for setting up the AV and the speaker tonight. I do have one more thing to share with you. It's a story. This guy goes into a library and he asks the librarian, he says, I'd like to find a book about Pavlov's dog and Schrodinger's cat. And the librarian says, well, that rings a bell, but I'm not sure it's here. Okay, so if you need that joke explained to you, talk to Jerry or Doug. So with that, again, I'll thank you for attending the meeting tonight and look forward to seeing you all again in December. So good night. Good night, Omar.